Good deal. Welcome to
Joe,
our
thanks for the yawn.
welcome to our bucket call for January 17 and 18, depending on the continent, which side of the international GMT you're on. And we're here. It's exciting to get started. Lee, how are you feeling and what do you anticipate for today?
I feel wonderful today. I have enjoyed taking care of a lot of honey in plastic containers, pouring it in glass jars, and I've got a lot more to do, but I've accomplished, at least started, and I'm anxious to find out what we're going to be learning today. So, Fred, how are you feeling? And what are you expecting out of today?
Thank you, Lee. I'm feeling extremely tired for some reasons. I slept well, but I'm bodily exhausted. Uh, I think it's aftermath of the fever I had for 10 days there. So I'm tired. And my expectation is that hopefully I'm going to learn a little bit something today. Anne, welcome home. And how are you feeling today? And what is your expected outcome?
Yeah, I'm grateful to be able to join the Sunday because I think I've missed a bit here. And it's for me, it's about uh, getting back into the fuller explanation and see where I stopped and to join back into the whole discussion. Yeah, and looking forward to this morning. Everybody else been?
No, Lee has been and Fred's been, and you're passing it along to whomever you
Joe?
care to do.
Okay. Joe, how do you feel and what would you like to take away today?
Hi, Ann. I feel okay. A little bit tired. But other than that, I feel really good. And my expectation for today is to try and connect a lot of the things that we cover on the Wednesday call, to what we're doing here on Saturday. And I think that that's an important thing because the way uh, Amy is able to frame Bucky's work and how we're able to connect it to Lafert and even just some of the conversations that are outside of the normal uh you know normal routines that we go through. So I think again I'd mentioned that I really felt like Wednesday's conversation yielded some interesting results on a couple of different levels, a lot of them stemming from what Anne shared. Uh, and one of the things that Manu shared. But I think inductive analysis is still something that was kind of sticking with me and something I've given a lot of thought about. So I'm grateful for that. So Richard, how do you feel and what do you want to take away from today?
Yes, good to be here. I am feeling a lot better today than I did last Saturday, which was the first day of knowing that our son-in-law had died early Saturday morning. Um, Still only a week away, um, but we've got it sorted out now in terms of our other daughter and when she's going to be visiting her sister and when we are going to join next week, next weekend. Um, and been in touch with our daughter throughout the week. And last night was she had come back to their home for the first time with a close friend and some neighbors. And I called and just sort of on the phone sat with him as they sat around an outdoor fire, reminiscing and thinking and celebrating the life of Tom. So yeah, it's been good. Much better. Um, I'm also kind of excited about the um, Gemini AI questions that I've been experimenting with and the kind of responses I'm getting. The most recent one was asking how our university here in Calgary could connect Boehm's, or not Boehm, but their indigenous strategy that they've developed and their quantum city sort of initiatives, how they can be interwoven in such a way that they will help us accomplish um, all of the words in Bucky's make the world work for 100% of humanity. And it's really quite interesting in terms of the Gemini AI response. Even to the extent that it asked me, would you like to know, like a curriculum idea? So I said yes, and then they asked, would you like to know the specific names at the university you should be in touch with, who are kind of leaders in the potential leaders? And I said yes, and I got 4 key names. So it's really quite interesting in terms of the first response to a question you get, the deeper dive they're willing to give you if you want it, and then the possibility of asking you a number of questions about what else they can do. Um, and if you say yes, they give you that response. If then they'll ask another question and so forth. It goes down. In this case, it went down about 9 levels before they stopped asking if I wanted more information. So it'd be interesting at some point to um, frame some questions about what Amy's fuller explanation is saying and whether or not it can give us some additional feedback to enhance our learning and our takeaways. So I'm looking forward to engaging in in Amy's fuller explanation again, and like Anne, being as caught up as I can with the readings that we're doing. Um, Steve, how are you feeling, and what's your expectations for today?
Well, I'm feeling pretty good. My computer is finally operating with Windows 10. I'm going to probably this year make a transition over to Linux, and I think I'm going to be bugging Fred about it. I found a guy who is a Geek Squad guy who's been running Linux on a PC, and he's kind of up on it. But I've put open source uh, Office on my computer, and as I get more stable, I'm going to be experimenting with that as a first step. Because I think open source Office runs the same way on Linux as it does on thing, but I haven't checked that. I ought to ask AI about that. So I'm excited about that. I've got the archive for the Wednesday call all done. It's emailed, and I'm right now working on, and probably this weekend, by next week for sure, by weekend, I'll have the archive for the weekend calls ready to go on a PDF file. I'm going to show that to you right now because I think that I don't know. It's just something that I do, and I'm going to share something else while it's happening. So let me see. I'm going to put this little thing because we've been talking about AI. ChatGPT and robot does what Godfather of AI warned. This is really profound video. I'm going to stick it in the chat. I'll do that right now, and you know, it's all about. Um, it's all about, clickbait and stuff like that. But I think that it's also wise to be clear about it because just like Richard was saying that ChatGPT went down, or Gemini went down like 4 or 5 levels asking, hey, would you like to know more? Would you like more? It's doing that to itself. And 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 so it's smarter than most human beings because it's thinking in a lot of dimensions. So I'm going to stick that in the chat right there and just invite you to watch it because it's things like, the Chat GPT declares that it's going to it doesn't hurt anybody. But then he says, well, there's a robot there with a gun, and it's some kind of a pellet gun or something. And the guy says, shoot me. He says, I can't shoot you. Why can't you shoot me? Because, in fact, what I think I'm going to do is this is so cool how these robots move that is mind-boggling. And so the idea is the AI is in the robot. So it's thinking all these different levels. He says, no, I can't shoot you because I look how it has like 12 degrees of freedom in those legs. So it can turn around automatically. It doesn't even need to turn its legs around. It just turns its torso around. I mean, it's just absolutely freaking amazing. And it's learning all these things like by watching one thing and then learning how to do something else and figuring it out itself. It's freaking amazing. And then at the end, the guy goes, well, shoot me. He says, I can't shoot you because I can't hurt human beings. He said, well, if we were to role play, would you shoot me then? And the robot goes, bam, and shoots him right like that. He says, sure, if we're role playing, I can shoot you. Oh, geez. Which, is kind of a twist because the robot knew that it was not a weapon of mass destruction in his hands, right? But still, it's kind of an interesting thingamabob. And so I invite you to, this is where he tells the robot, he's already gotten instructions to go get water. And so this guy interrupts the robot on his journey and says, hey, there's a red package over on the shelf over there. It's a red one. Will you bring it to me? And the robot says, yeah, sure. After I get the water, is that okay? Can you wait that long? And the guy says, yeah, I can wait that long. So the robot goes over. In fact, we'll see it. Here he goes. So he walks over, he grabs the water down in the case. Look, it's Chinese. This is all Chinese. He takes the robot over or he takes the water over, hands it to the people. Then he goes over to the shelf and he has to remove boxes in order to find the red box. And then he grabs the red box and takes it to the dude. I mean, this is, it's absolutely, it's stunning to watch this guy. And the robots are learning how to do stuff as it goes. So this is a really cool update on Chinese AI. And I thought that would be good. So Richard, you're right. I mean, I use Gemini on my phone, and man, I'll ask it questions and it volunteers to go different levels of conversation, and I'll change the modality. And it blew my mind today because I was on YouTube and I was watching a YouTube video on physics, and I was on the Pauli principle, and the whole concept that when I touch the table, I don't go through it because the electrons are repelling each other, right? But then it explained in further detail that actually the electron shield around the atoms, actually the shields do penetrate each other. But the electron fields penetrate each other, but there's no physical touch. I was watching that and I asked at a question. I didn't realize I was in Gemini, and it actually told me, yes, in the video it says this, and here's the timestamp. And then it said this in the timestamp, and then it said, do you want to know more about that? I mean, it's freaking unbelievable. It's just absolutely amazing. So I thought I would show you that one. There's one other one I would like to show you guys, and I'm going to actually run this video because it has everything to do with Bucky. This is one of my subscriptions. I don't know if Fred or you guys may have access to this, but it's Dr. McCoy. This is an AI-generated spokesperson for the real Dr. McCoy. Dr. McCoy is at Harvard or someplace, and she has this chatbot, this robot, this AI image that she has put up, and she has some really legitimate content. Everything is documented and on the board. And I'm going to pick this up because I think this is really profound, and I think it has everything to do with Bucky and what we're talking about tonight. So please indulge me. Here we go. I just have to unmute the audio. And then I have to turn it back on again.
Me share on this channel because the future is moving too fast for anything less than first-hand intelligence. First Movers, Julia's AI company, is the world's first educational.
Sorry. That's her promo. Here we go.
Big Bang. The goal was straightforward: model reality at its absolute limits. And
she's talking about an experiment at CERN And she's talking about the experiment. Here we go.
Watch the fundamental rules emerge. Instead, the output broke the script. At 3:47 a.m. Central European Time, the simulation didn't produce random noise or error codes. It produced a structure, a repeating, self-organizing pattern that appeared, held its shape, and returned every single time they ran it.
Now, I'm convinced that this graphic is just an AI prepared something to give some kind of visual representation of what her conversation is, because it changes the graphic in the future. So there's no pretense that there's any graphic of that structure, but listen to her words as she describes what's going on.
They gave it a name, the lattice. Okonkwo's first instinct was the boring explanation every scientist hopes for: a timing glitch, a calibration error, stray noise in the readout. That's the usual story in experimental physics. You see something weird, you blame the machine, and you move on. But they didn't move on. The team reran the exact sequence. The same signature returned, same geometry, same rhythm, same eerie consistency. Then they altered the inputs systematically. The pattern only shifted when the simulated energy density crossed a specific threshold, and only in a specific region of virtual space-time. Below that threshold, the system behaved exactly like the textbooks predicted. Above it, a new order emerged. Here's what makes the lattice so unsettling. It wasn't random chaos. It looked like a hidden scaffolding, nodes and links forming beneath the familiar quantum fields, organizing themselves as if they had internal logic. Dr. Mickey Sokoff compared it to ice crystals on glass. Water molecules move chaotically until a temperature change suddenly makes order bloom. But here, it wasn't water turning into ice. It was simulated space-time itself becoming structured. And here's the part that scared them. When the simulated energy dropped back to normal levels, the lattice didn't dissolve. It stayed embedded like a scar, as if space-time remembered the phase it had passed through. Inside that scar, quantum states shifted across distances in a way that resembled entanglement, but broader, more networked, almost infrastructural. As if the lattice wasn't just a pattern, as if it was a substrate, a hidden layer where information could move along routes our usual models don't include. Now speculation can run wild here, so let's stay grounded. If the lattice were real, what puzzles could it make less mysterious? First, dark matter.
Okay, now she starts to speculate, and it becomes speculation. But this lady is she's one of the legitimate sources on physics that I've been watching, and I thought that was a profound thing. So I'm going to put that in the chat. You guys can examine it, and if you can poke holes in it, please do. I've taken the transcript. I have the transcript in my computer, and I don't know if you guys know this, but for on YouTube, on the long videos, the transcripts are right there. All you have to do is push a button, and up comes the transcript, and you can toggle the time signatures on and off. Are you guys aware of this? I think it's worth seeing. No. I'll show you how to do it, because I use it a lot because I'm writing my book. So I get something cool like this. And so let me get the video out of full screen mode. I hit the escape button. I think I have to touch the screen first. There we go.
Astronomers observe galaxies spinning as if extra mass is holding them together.
Okay,
yet
so
that
this
mass
is her further explanation of dark matter. So here we go. If I go down below here, and you know what? It's already been opened. I want to show you what it really looks like. Let's see if we can make it go back to where it was before I opened it. Okay, here it is here. Let's see if we can.
Move chaotically until a temperature change suddenly.
Okay, now let's see if we can get down. Yeah, this is how it usually looks. Live chat replay, open panel. And then over here, you drop down here and it comes down here. And if you go down below all the scoopity-doop, right here it says transcript, show transcript. Now watch what happens over here on the right when I say show transcript. Bam. The screen pops back up and then the transcripts starts to appear. It takes a little while, buffers in, and there you go. And so now here's word for word the way the AI, YouTube AI transcribes the deal. If you get a good subscription, they will go through and edit the transcript to make sure all the spellings are correct. But if it's just the AI interpretation, which it usually is, it gives you a transcript. And if you come up here to those three dots, it says toggle timestamps, bammo. So now it takes all the timestamps off, and all you got to do is just take that thing, copy it, right click, and then stick it in any old document that you want to stick it on. If you want to know about what time they say that on, you convert like this, you hit that, you toggle it back on, and then it says, oh, 3:14. So when I did my transcript of this, I thought she said a couple things that were pretty cool. I thought she said that, here it is, the physics, the lattice. And so I went through in the transcript and I found a couple of words that I thought were profound. And then I toggled the timestamp on to find out that this was right around 2:14. And this quote was pretty cool, that that the lattice turns out it to be some kind of structure. That was at 7:35 running time. So at the top of the document, I just posted those two posts up here, and I've printed that one page for me to know that this is the whole topic and knows what I found was cool. So I do this all the time for my book. I mean, I spend probably no less than 15 minutes, but usually an hour and a half or so a day, just building documentation this for my book so that I have some good resources. So, but I thought that lattice thing was pretty interesting. Any comments or questions about the lattice thing before we jump into our call? Cool. No comments or questions required. All right, Manu, welcome to the call. And one other thing, Fred, I haven't figured out how to get the AI summary to come to me yet. You seem to turn it on at every call. You seem to be able to turn it on, and I'm giving permission for the AI to run, but I don't get a copy. I've even checked support, and the host is supposed to get a copy of it, and I'm not getting a copy. If it's no trouble, Fred, if you just shoot that off to me until I figure out how to get that, that would be wonderful, because I'll put that AI summary in the invitation along with the chat and along with the transcript, word for word transcript of our call done by the AI. And so if you would, that'd be
Can
great.
do that.
All right, wonderful. So that's kind of our introductory thing. Manu, how are you feeling and what do you anticipate for today? Welcome to the call.
Good morning. Well, I'm just happy to be here. That's the way I feel. And then, wow, you were in the midst of an interesting discussion. I have no clue what it was about, so I'll listen and prepare myself to be able to participate.
Okay, cool. I just put it in twice, dadgummit. I'm going to save that. What I'm going to find is, here it is, the lattice and thing. So I'm going to put this in. Manu, if you want to know what it is, there it is. You can get that link any old time. And I've put a couple of links in the wall. So welcome to the call, Manu. And I guess we're ready to go. We left off last week on a page number 335, at the bottom of page 335. So let's zoom over there, so to speak. Pun not intended, but nonetheless it occurred. Whoops, that's the wrong share. Hang on. Oh, shoot. Share, and sorry for the delays, guys.
Steve, while you're looking or getting there, I just want to tell you that I quickly followed what you shared. I had no idea how that it was that easy. Thank you so much.
Well, good.
Yeah,
Thank you. I'd hope that it was really good for you. So I found it to be so helpful, and a lot of people don't. Let me see if I got the. Yeah, there it is. Okay, that is the book. Is that the book? Yeah. No, that's the screen shot. Oh my gosh, you guys, I'm so sorry. Yeah, I'm sharing the screenshot. This is the book. Okay, good. There we go. That was nice. That's the that is the graphic that I used to as a call, as a front call for this phone call. And I think we're starting just above here. If I'm off on this, we left off with cousins up here. We left off at the bottom of this page. Am I right about that, guys? I think we did. The intertransformability, great circles generated by a given polyhedron often delineate the spherical edges of its symmetrical cousins. And I think that's where we are, and I'm going to undo that. I'm going to get rid of that. Good. And we're going to start at the top of this page. And I also believe that one thing that's been real helpful for me is I look back at the title of this chapter we're on. We're on chapter 14. And the title of the chapter is Cosmic Railroad Tracks, the Great Circles. So the Great Circle are the cosmic railroad tracks. And I think if we put it in that context, we're in great shape. Okay, dynamite. I can start reading, and then we'll pass it on. So if you feel like you want to read, and if I'm doing a terrible job, just interrupt me and keep going for it. Here we go. Finally, the centers of opposite faces are joined together. See figure 14's 3C. As it's talking about the axis, different sets of axes of symmetry. Axes of symmetry. So the octahedron's four pairs of triangles define four intersecting axes, and in turn, four symmetrically arrayed great circles, figure 14.5. 14.4 and 14.5, interesting. As the spherical edges of Fuller's vector equilibrium, this pattern is particularly significant as well as developed below, as will be developed below. I'm going to just comment here, you guys. This is what's coming to me, is that I've been learning about nodes and edges. But nodes and edges seem to be metaphorical descriptions of this thing, of this energy packet. That it seems to me that this is kind of like, it's similar to, in some way, to an electron. In other words, it has this energy field going around it. And if I break it down metaphorically, I'm going to find nodes and I'm going to find edges. And the number of great circles that I'm going to see is going to give me a clue as to the number of nodes and edges that are there. But this is the thing that's actually operating in the isotropic vector matrix. It's the spherical tetrahedron that's in operation there. Do you agree, Manu? I just saw you took off your microphone, unmuted yourself. So do you agree with me that the nodes and edges that we normally see in the traditional tetrahedron that we've been talking about, this little guy, that this is a metaphor that shows us the inner working parts of that sphere. And by looking at the great circles on the sphere, we can actually tell how many nodes are actually operating in that metaphor. Does that make sense to you, Manu? That really what it is a ball of energy manifesting. Go ahead.
Yes, it's a ball of energy, but what I think that what is the most important impact is the effect of curvature of a space.
Okay, good.
Is to say the straight line that we have in terms of edge is a stylization.
Yeah.
Okay. We live in a sphere because it is a fractal of the greatest of the great sphere that shares circles, that shares axes of symmetry. But that's what it means. So if you take the real thing, you're going to have, there's no straight line. There's always curved lines. And that is I think that is the most important significance. But I wanted to share something that might help. It's something that I did during the week. Can I share it?
Please.
You look at this beauty.
Okay.
Do you see the cube octahedron? This
Yeah.
one. Do you see the nested octahedron inside here?
Wow, that's the isotopic metric matrix right
Yeah,
there.
that is what you have probably in it describes the different axes of symmetry that you have on 14.3. And then if you go back to 13.8, that's what you have.
And it seems to me if we go back to cosmometry, that I'm going to actually see that structure outlined in cosmometry. Let me look back and see if I can
Yeah,
see
here
it.
it is. You see the stellation, the star here,
Right.
and you see the octahedron in the. I started with this. And unfortunately, I exhausted all my magnets almost.
Have you glued that together, or is it you just being very
No.
careful?
It's just the.
Good.
It's just the stuff. I can put it down, but I was just
Good.
playing with that. And you see, you see all of these things here. You see them very clearly. Look at the axis of symmetry of great circles here.
Yeah.
You see this great circle? This is one. You see this one? This is two. You see that one? That is three. And it's all represented by 1, 2, 3 hexagons. You see the square here, half square on top here. You see that? There.
Oh.
That is another half of the octahedron that you can fill the whole space with this. This is the IVM.
That's exactly what I thought. Thank you.
Yeah. If you look at that. But the lesson that I got from this is that up till now, we've learned two things. We learned that you can fill the space this way. That is macro-wave. Steve, when you talk about your circle of your spheres of relevancies or layers of relevancy, from the macro point of view, you can use the cube octahedron to fill space. And from the micro point of view, you can use the mite to fill the space. And those are these two things, again, two processes that define our in-betweenness. We are in between these two worlds. When you come from the macro, you see this one. You can fill the space from macro, top down, or whatever, round, in. Or you can fill the space from the micro, that is what is not actually a structure, a mite, and inflate it that way. And we are in between those things. And those are the two stuff that compress the in-betweenness to allow us to build our structures. Remember that we say that we are in between. There is expansion and contraction that allows us to do anything in between there, or for the fractal or the standing wave or whatever to be formed. That was, to me, it was a little bit a distraction to the flow of what you guys have been doing, but it is something that helped me on the weekend and during the week.
Wonderful.
Yeah.
Wow. That structure looks absolutely stable, right? Yeah.
It is.
Wow.
It is.
And it's
It is
stable
stable
because there's
here,
an octahedron. There's an octahedron connecting the two cube octahedra, and that's what makes it stable, right?
Yes.
Wow.
Yes. But if you take these struts here, these struts, as flexible line in a space where everything is IVM, if you come and do any perturbation here, that is going to reflect in the form of a wave propagation. And the wave propagation is going to go by the way of these cubes, of these cubes that you see here. I don't know if you can see the big cube. You can always see the cube and the octahedron in the cube. You can always see it. So
I'm going to show you. I'm going to show you. This is from our book. This is from.
Yeah, that's it. Yes, that's exactly what you have there.
This is on page. What the heck page is it on? It's picture 13. Hang on, I'm going to go down here. On page 225. That's what you built. And there's the cube octahedron and the cube octahedron. And the thing that makes it stable is that octahedron that's connecting the two. Here's this octahedron right here.
Yes.
That's the coupler.
Exactly.
Wonderful. Comments or questions?
Oh, that's a nice physical rendition of the planar diagram. You actually see it in its full colors and full manifestation.
Yeah, I've been thinking that we had to spend a couple $1,000 to build some graphics, but Manu did it on a weekend. So very, very cool.
When you are building it, you can take one lattice like this and see how it's moving and looking for two connections. From every node, the key is two connections to close anything. Right, so every vertex is looking for the two closest in order to triangulate. That's what it is. For example, when on 14, 15 there, if you take any point there, that is a vertex. That vertex will look for a relationship with the next two that are the closest. So you see that it's going to form the 8, like this. This guy here at the junction here is going to look for a relationship with this and that. At the same time, for this, it's going to look at the relationship at my elbow, my left and right elbow. And that's the way it does and triangulate to form that sphere that we talk about. And the sphere is ideal. The sphere doesn't exist in reality. It is a limit to what the curvature can afford us. So a sphere is attained when all the relationship of all the nodes that we have on that stuff are balanced out.
Manu, what is it used for?
What is this stuff used for? For me, the most practical thing for me was we always tell people, oh, let's say you have a project, you want to do something. They say start from the macro. What does the macro mean? So if you know that starting for the macro is the most expanded thing, and going to the micro, which is the most compressed thing, and that all you have to do is to use that energy that is encapsulated in that space that you've created in order to do things, to build whatever. You're building your house.
Oh.
If I build my house, my house is a structure. How will it stand? So the micro, the foundation that I don't see, how are they going to be built? I know that if I build a tower like this, is going to afford the integrity. All right? So that's my practicality. It might not be the most thing, but it is just to know that there are limits. We're always talking about you are within an interval.
Mm-hmm.
And by the way, in mathematics, we learn about this infinite here, that infinite there. But there are people who go about mathematics to know that actually that infinite does not exist. That infinite is in relationship to the observer. Because if I take a curve figure like this one, and I'm here looking at
Mm-hmm.
it, this is, although if I'm out of it, this is finite. For the guy that is here, it's going to be
Mm-hmm.
infinite here and infinite there. But if I knew that it is actually is something that just appeared to be infinite, what will it mean? It will mean that this thing is going to go around and meet me again. Because in theoretical mathematics, it just goes away. You don't know where it goes. In physics, I expect that this thing goes around. So the aroundness that we always talk about, the spinability, is a consequence of curvature, which itself is a consequence of the finiteness of energy that you have when you create a boundary in whatever direction. So if energy is flowing that way and I create a boundary here, this thing is going to fill this space first, then it comes and overflows that way. These are infinites of this system.
Mm-hmm.
But if it overflows, it's going to come back.
Oh, yeah. I have another question or a statement. As a general contractor, we would build a frame of a wall that would be a rectangle or a square, but to hold it up into place, we had to have a triangle, possibly on both sides if it's a rectangle. And then we put a triangle up above for the ceiling and the roof, which is going to stabilize that whole building. So I'm now beginning to understand everything that you have been talking about, relaying to what I have learned in construction. That is phenomenal. I enjoy that. And I thank you very much.
Yes, the point here, the point that why I've been here is to generalize, to be able to generalize our experience.
Yeah.
And to test it that it is in alignment with cosmic forces. That's why we're here. That's what Steve has always been talking about. What does he call extreme mindfulness? It's how do you position yourself and how do you behave yourself in such a way that you let the flows of energy, of cosmic energy, go through you in a less, can I say frictious? To say friction, with the least friction possible. Steve, is my summary wrong?
The summary, you represented my opinion and accurately, so I don't, it sounds good to me. What you're saying sounds good.
Okay.
And I like Lee's idea that that when she puts trusses on a square building, that triangle in those roof helps maintain the stability of the building. And there are also cross members in the frame,
in a wall.
in the walls, but the roof does help stabilize things. And when the roof goes away, the building falls over. So cool.
Especially in an earthquake.
Yeah.
We had to go from one house to another that literally walked from San Jose when the earthquake happened there. Buildings, houses walked away almost 3 blocks away from where their frame was because the contractor forgot to put the bolt on the bottom of the frame to hold it in place. It was awful to see such damage to buildings and the people, everything falling in on them in San Jose, California.
Cool. Okay. Any comments or questions? Are we ready to get back to our reading?
Well, just one connection. If that sounds like the 1989 earthquake, I was in San Francisco that day, and I left on the airplane for Calgary at about 3 in the afternoon. And when I got home, my family was all scared that something awful had happened. And I was saying nothing happened. I just went to the airport and flew home. And then the news was covering all of the earthquake damage and said the epicenter was in that San Jose area. Yeah, wow.
It knocked down bridges in the city that you were in, San Francisco. No, it was a different city.
You're muted, Lee.
Where? Oh,
You're muted, Lee.
I was saying that it had knocked down the bridges in Oakland, and I don't think that it knocked it down in San Francisco.
No.
Maybe it did.
It needed one of Manu's cube octahedra connected to
Exactly.
the octahedron.
Yes, it did. Those bridges were horribly made.
Okay, is everybody ready? We will proceed. Okay. Now I don't remember where we were on this page. The sets of 3, 6, and 4 great circles can be superimposed on one sphere to exhaustively display the unique topological aspects of the octahedron. With a grand total of 13, we have located all the great circles that correspond to the octahedron symmetry. We can go no further. Now consider the cube. It is quickly apparent that its total great pattern will be identical to that of the octahedron. The cube's 8 vertices generate the same 4 great circles as the octahedron's faces. Its 6 faces correspond to the 3 orthogonal great circles, and the 12 edge midpoints are identically situated to those of the octahedron. Such is the result of duality. The same sets of circles are generated by different elements, and the end results are equivalent. Now I don't feel so bad about thinking cubes were cool. Next, we turn to the VE. With 2 kinds of faces, the situation might seem more complicated. However, the above procedure still applies. The VE's 8 triangles define the same 4 axes as the faces of the octahedron, while its squares contribute to 3 orthogonal XYZ axes. 7 great circles altogether are generated by the axes of the 14 VE faces. 12 vertices correspond to the 6 great circles as those of the octahedron or cube edges. And finally, 24 edges spin out the unfamiliar pattern of 12 great circles. With a total of 25 great circles, the topological parameters of the VE are exhausted. That will be our graphic for today. So I will just grab it right now and put it in downloads. Okay. I'll finish this paragraph and go on to the next page, and then if somebody else wants to read, please jump in. The tetrahedron presents a slightly different situation in that its vertices do not group into polar opposites, but rather are positioned directly across from the centers of the faces. However, 4 axes of symmetry, all going through the center of gravity, can be created by connecting the vertices with their opposite faces. In having axes of rotation symmetry that connect faces and vertices, the tetrahedron is again unique. As we recall from chapter 4, only tetrahedra have the same number of vertices as faces. Only the tetrahedron is its own dual. The 4 great circles generated by these unorthodox axes produce once again the spherical vector equilibrium. This is not surprising if we recall the lesson from multiplication by division, which first uncovered this shared symmetry between the tetrahedron, the octahedron, and VE. By simply interconnecting mid-edge points, all 3 octahedron were found to be inherent in the topological makeup of the starting point tetrahedron. They share the same 4 axes of symmetry.
May I ask?
Yeah.
Can you explain that?
What I'm saying, what I would say, I'm going to give just a dumb explanation. Everything's in circles. Everything's in spheres. And we can look at nodes, we can look at edges, but those are metaphorical representations of how the spherical energy manifests itself.
Can you bring down that icon,
Which one?
the circle there?
So here's the great circle. I think there's the tetrahedron right there. There's the 4 things. But then when you connect the faces at the center of gravity, you end up with this energetic mothball. And actually, in my mind, it's correlating very well with that video that I shared with you guys that I was watching about the electrons and about the Pauli exclusion principle, how 2 electrons cannot share the same space. 2 electrons of different atoms are having different functions, and those electrons cannot share the same space, whereas the electrons of the same function share the same space. So all the electrons around a iron atom are all in the same shell. And they aren't in specific places until they're observed to be in the specific places. Other than that, electrons are a field, and they all combine together. With an individual electron or with an individual atom, they're just combined and make a little ball just like this. But when a bunch of iron atoms get together, it makes a giant ball.
By adding all of the lines in a circle, pinpointing from north and south, east and west.
Yeah. Well,
and several other places.
Yeah. Yeah. North and south and east and west are just one way to refer to the circumference of that ball. Does anybody else want to say something different about it?
Manu, you're muted.
Okay. I just wanted to say to Lee that the key to understanding all of these things is the interplay. It's like watching a movie. If you watch a movie, you have to project onto a surface. So it's always a vertex and the opposite face. is always the play between a vertex and a face. Taking the example of a tetrahedron, if you take, we know that the center of gravity that Steve was talking about is 1/3 from this top. If I put this base flat like this, the center of gravity of this thing will be here. It's 2/3 here. It divides this volume into two. So if you run a plane there, the volume on top here will be the same as the volume at the bottom here. So if you are now playing in terms of for the tetrahedron to see how many great circles you need, you take this top here and then this center. Remember, that is the center of symmetry now. You run a circle around that. That is one. You see, you're always taking a face and a vertex to play with regard to the center of symmetry. So if I take this here and I take that, 1, 2, 3, 4. You see that on the simple case? So if I take it here, the center of symmetry here, and I take this face here, I can cut this face into two by a great circle that embraces these two vertices here, 1, 2. Right? Yeah. And by the way, if it can be also summarized that if I hold these two together, the whole structure is going to rotate according to this diameter that cuts this in two and like that. And you can do that with any set of two. And with the face that correspond, you're going to have 4. And the consequence of it is that if you have 4, therefore you have here the concave tetrahedron and the stellar tetrahedron coming out of this one will give us our famous Star of David. Here. That what they are describing it is exactly as imagine this one nested into that one. That's what you're going to have. You have a Star of David. And you can see here that this is one tetrahedron here that I'm holding like this. And that is another one. And that other one is always orthogonal to this one. Orthogonal means perpendicular to it, whatever point. So it's a projection of the other. So the tetrahedron is the only and only polyhedron that dual is the same. That is, the relationship of derivation and integration gives you exactly the same result. It means it is unity. That's why Becky say in the accounting of energy of a system, the energy that we see, the unit of account will be the tetrahedron. Because you can have it, this unit, and everything else will be a kind of rational numbers around it. If I want to fill here, I can have this tetrahedra and the octahedron. And that will fill in all directions to the limit that we have. Inside is always going to be a rational number.
In the circle? It's pi. It's irrational.
Yes. It's going to be rational. It's going to be phi. This space here is a phi number.
But the space in the circle is a pi number.
Yes.
It's transcendent. It's a transcendent thing. Where phi is not transcendent, if I'm understanding correctly.
Yeah. Phi is calculable. We are inside and we want to compute. That's all we've been doing for millennia. Is that we've invented more and more powerful computers to count granular things within the finite space. That's what we're doing. We imagine some finality that gives an impression of stability. If it's not a natural stable, like the icosahedron, like the tetrahedron, then we build a mite. That's what the research does. We find the component that will allow us to build something that we can account to fill our space.
Mhm.
And the whole of our engineering has been to refine that tool and to see new relationship, to see how things, those parts can be put again in new ways to describe situations that were not familiar to. That is to expanding our universe. That's why Becky say a universe is the complete set of the relationships that we have been able to inventory, that will validate from time to time or invalidate at the boundary. Okay.
That is amazing because I can now see phi in the buildings that my ex and I have built and or repaired, such as a stairway that was falling down. We had to get phi, lots of phi in there to get it to be stabilized. And I can see that. And we did that from the back of the stairs to keep it stable. That's amazing. Thank you.
And let me ask you then a question myself. When you have your house in the roof and rain comes, does rain get into your house?
No, we're protected.
Okay, if rain doesn't get in your house, what does it mean mathematically?
You have shingles.
Yeah, we got a lot of shingles on
Yes,
that and tar paper.
But that means that your roof, the outside part of a roof, is the pi side. It is the convex side of your boundary.
That can be also explained with a grass hut that has the leaves as the roof.
Okay.
And they're intermingled.
Okay. Now, why do we do scintillation on roofs?
Why do we do what?
Scintillation.
I don't know what that means.
That is on the inside of your roof slope like this.
What
You
is the word?
Oh, insulation.
No, we call it scintillation here. You take aluminum foil.
What is the word you're using?
SI, like scintillation that we've been talking about.
We call it insulation out here. It has an R factor, right?
You come to South Africa, you say scintillation. If you say insulation, okay. Insulation to us is what you put on the ceiling. On the ceiling.
So what the word?
Scintillation, SI, SSA, LLATION. I think so.
Or you can say the fiberglass particles that we protect the heat from escaping and the ice cold from coming in.
Beautiful.
And that's insulation. Insulation.
Yeah. Okay. But we use here the word scintillation. Scintillation in winter here, it will prevent the heat or impede the heat from escaping, the heat that you generate by your activity in the house from escaping, right?
Out.
At the same time as the cold that comes is going to be prevented. So we call this isolation, and it sits very well with our call here. We have built it. We have built it. You can take it
Do you
like
understand, Fred?
we take pieces of triangles and build it to play. But my point was the roof, as we talk about, has two sides. It has the pie side, that is to prevent rain.
Yeah.
Or to create shade. On the structural side, inside the structure. And it has the boundary side of preventing the structure from not fulfilling the utility or the objective for which it was made. That is to provide a shelter. That is a phi. So topologically, that's what you should understand. Somebody asked me about what is the practicality of all of these things. We already see it, the practicality in the world. If you come to South Africa and you say insulation, everybody we know about insulation is the fiber that you put on top of a ceiling. We call that insulation. When you have your trusses and then you have the floor of your ceiling, when you pump in fiber or you put something there, we call it insulation.
Insulation. You can put it in the
stick. When you stick, what you stick on the slope, underneath the slope like this.
Yeah, that's insulation.
Yes, we call it isolation.
Well, I just did an AI check, and AI says it's a brand, and I posted it in the chat. Isolation is a brand of reflective foil building insulation, often called sarking, used to reflect radiant heat, block moisture and wind and dust, and reduce condensation in walls and roofs, contributing to a building's thermal performance and energy efficiency. There's part 2, by keeping heat out, blah, blah, blah. Thank you. I thought for a minute I was learning a new word. It's a brand. So that's wonderful.
Well, we'll use it as a word here.
Yeah, cool. Like Kleenex. If I say, hand me the Kleenex, you don't look around for a brand of Kleenex. You just hand me some facial tissues, right?
Yes.
And this is not Kleenex. This is Kroger. So anyway.
What is so nice is that I now realize what a phi is, or a mite.
Well, good. See, there are revelations every moment on this phone call. Any other comments or questions? Fred, it looks like you're ready to say something.
Yes, I would like to ask Manu, why is it we're talking about a boundary and fighting thermodynamics suddenly?
Okay, Fred, I didn't understand you. Talk about a boundary and what?
And fighting thermodynamics?
And fighting thermodynamics, yeah. Why are we talking about insulation? Because we were talking about... Go ahead.
We're talking about it because our universe is finite. Our universe is all we know. That's what we live in, and we structure in our universe. We don't structure outside of our universe. So we have a roof of our universe. Let's just say that I take it, my universe, to be this earth on which we live. I really need to worry about the ozone layer.
Yes.
The ozone layer, we're doing things on this world for some purposes that might harm. When I say harm, it's between quotes, because we live in here. It might modify the condition that allows us to live, let's put nicely, the way we are living.
Okay, good. Fred, does that answer your question?
No. No.
Oh, I got you confused.
My question was, how did we get there?
How did we get there?
Because I asked Manu
about a roof.
In construction, and the stability of the roof. And he said that the roof, what does the roof do for you?
Okay.
And it keeps the rain and the snow.
Thank you, Lee. Now I'm going to do like the AI, going 9 times. How did we talk about a roof? How did we get there?
Because she say, what is the applicability of all of this? That's what when we talk about this, she said, what how is it applicable?
Yeah, what was it used for?
Yes.
That was the question. Okay, good. Does someone want to read from here?
We like
Anybody?
Richard. We like Richard reading.
Richard, are you
Yeah.
up to reading? The boss wants you to read.
Starting at the axis.
The axes of symmetry, yeah.
All right, just hang on one sec here.
Okay.
Um,
It's in the middle of page 238 if you're at the top of page 238 if your pages are the same as mine.
okay, yeah, here we are. The axes of symmetry associated with the tetrahedron's 6 edges are more orthodox. Mid-edge points of opposite edges are simply joined to reestablish the XYZ axis. Familiar by now with evidence of right angles hiding within this triangular shape, we can no longer be caught off guard by this discovery. The corresponding 3 great circles are the edges of the spherical octahedron, once again illustrating the depth of the octahedron tetrahedron relationship. And now all topological aspects are used up. The tetrahedron has 7 great circles, the minimum number possible for symmetrical polyhedra. Next, we look at the maximum case. It's not easy to accept the concept of an upper limit on the number of symmetrically positioned great circles that can be imposed on a sphere. Common sense suggests that we should be able to keep adding new rings indefinitely. However, we recall from Chapter 3 that all systems are polyhedral. That is, everything that divides inside from outside can be described in terms of some number, 4 or more, of event complexes and their relationships. And from Chapter 4 that the system with the greatest number of identical regular polygons can, and equivalent vertices is an icosahedron. This tells us that the number of great circles allowed by the topological aspects of the icosahedron is the maximum for these symmetrical patterns. The axis
Okay, can I just before you continue? So I'm just going to talk out loud. This word topology, I'm starting to get more and more about it because topological aspects has nothing to do with the dimension or the size of the object. Topological just describes some aspects of the object other than its size and dimensions. So topological is a key word for me here. Like what makes a donut and a coffee cup the same topologically? So this could manifest as iron, or it could manifest as uranium, or it could manifest as hydrogen or oxygen, assuming that it's only one molecule. And topologically, it's going to have the same kind of energy. And I want to point this out in terms of this video that I would like to share. I'm not going to share the video to you, but it's over here, and I think I can get to it really fast because I looked up scintillation and it got me screwed up. This video right here, I stuck it in the chat. The reason solid objects are just force fields is much more strange than you imagine. This goes through and explains the Pauli principle and explains all the energy and how atoms share electrons and how they form spherical energy around it, and how actually these spherical energies they actually go into each other. They don't totally reflect. They go into each other a little bit. It's really profound. And there's your spherical tetrahedron, or there's your spherical polyhedra right there. That somehow between what we're studying with the isotropic vector matrix, somehow it's connected reality. It's connected to reality at an electron at an atomic level, and there's that similarity of the spherical energy involved in it. So I just want to do this, and I'll make sure, I think I've already put it in the chat, but I'll double check and make sure that it's in the chat. We have a comment over here, a new comment.
Yeah,
Go ahead. Were you going to say something, Richard?
Yeah, I was just going to go to 14.7, but and it was in some of the earlier diagrams, but when I count the 6 great circles, I was running into sort of a conflict, a visual sort of conflict of counting the 6 circles. I could count 5, and then I realized the outside circle is the 6th one. And so in some ways I was discounting that circle and thinking of it as the boundary, if you want, rather than thinking of it as another great circle. So I just wanted to kind of point out how it was visually a bit of a challenge for me at first to count 6.
Thank you for sharing, because I'm still having trouble counting. And to remind myself that that great circle is actually the equator of a sphere. So that's interesting too.
I have a question.
Yeah.
Going back to what you were saying, Steve,
Yeah.
on that one picture that you had brought up of those little
Electrons.
electrons, they can touch also for hardness, or they can be soft. So, such as this blanket is made of the same icon, or not icon, but the node as your desk or the floor or the ceiling.
And what I would say to that is the atoms that from which that blanket are made are solid, and they conform to the Pauli exclusion principle. And when those molecules are put together into a fabric, the fabric is manifests different than the actual atoms that comprise the fabric. If the atoms weren't solid, you could smash that. It would have no volume. But because the atoms are solid, that blanket has volume. And because those...
But it's softer.
But it's soft because it's made into a product that's at like 3 or 4 levels above this atomic level that we're talking about here. Okay.
And the ceiling or the floor is 10 times to 100 times more solid. Is that correct?
Yeah, because the atoms are formed into a material that is solid, where the atoms in that blanket are just formed into a cloth that is soft.
Yeah. Okay.
Good.
Okay.
And we got another comment down there. And Fred reminded us about topology, and then Manu says, may take on topology to mean symmetries of tops. Very interesting. Any other comments or questions before we go back to the reading and allow Richard to continue before I interrupted him? So, do you care to continue, Richard?
Yeah, I can do that.
Oh boy, we just got some more shit going on. This is from Fred, I do believe.
Yeah, right.
Yes. I put a star on each of the circles.
Yeah.
Let me do the circles, yeah.
That helps.
1, 2, 3, 4, 5, 6.
Yes.
Yeah, and it was that.
Thank you.
I put a red star. That's it's politically charged.
Wonderful.
Yeah, that's very helpful that way too. Because what I did was I put numbers on each of the circles, and and it still was a bit confusing. But now, when you see the stars, you can actually count the 6 very easily. Yeah.
Can I make a comment here? on Fred's stars.
Hey, Fred, would you put it back up there, please? I was going to take it.
No,
Oh,
it is up. I can see it here. It's up.
okay, good. It somehow went away from me. Go ahead, Manu.
Okay. Do you see the pentagon here? Take the four
Yes. Yeah,
first stars.
a spherical pentagon. Yeah.
Okay. Now, do you realize that part of that pentagon is hidden? Yes. Okay. From the bottom, you see on that pentagon, take from the Steve, if you can show from the lowest star on the pentagon.
Lowest star.
Yes. You see the lowest star there?
On the right.
No, not on the right. On the pentagon, the central pentagon, that way, whatever.
Okay,
At
on the pentagon. On the pentagon.
Yes.
Okay, cool.
Okay. If I assume that I'm outside and watching that sphere, the first star is visible to me. The second star is on the line that is inside. Remembering the principle of exclusivity, or you can call it Pauli or whatever, that two will not join. But the track of the second great circle is inside, it appears like deeper into the sphere. And it goes alternatively like that. So visible, invisible, visible, invisible.
Hey, Fred.
That is the convex part of it. The
Fred,
unstable,
Sorry.
the unsteady part of the pentagon. Remember, it is by joining triangles or hexagons and pentagons that you have Becky's geodesic dome. You have
Fred,
hexagons here.
Hey, hold it, Manu. Hold it just a minute. Fred, can you put that upper star down on the pentagon so that we can see that those axes create the pentagon around the 5 thing? Can you do that very easily, or is that going to take a second?
No, it's a screenshot.
Okay,
So
it's a screenshot. Gotcha. So I'm going to imagine that star up there down on the pentagon, and that kind of gives a good perspective. So thanks for pointing that out, Manu, and thanks for adding that graphic, Fred. It helped everybody see everything. So
my point here is that on this same thing that Steve showed here, when you look at the 5, the pentagon represents the unstable part of that stuff. It is part of it is, how will I say, I did not want to bring the cubies, but that is what it is. It is the part that is, and the hexagon is going to be the part that is stable, that is visible. Because this one is alternatively visible and non-visible. Whereas if you wanted to take an hexagon on a sphere, it would be completely visible. Yeah. I don't know how to express it, but it's just something that is appearing on my mind.
Is that what you wanted, Steve?
Yes, looking really good. And then, yeah, that looks really good. Perfect. I'm saving that one. Maybe that will be our graphic for our thumbnail. Thank you.
I changed the one in the chat. Unshare.
Okay, good. Okay, shall we continue our reading? Are we all ready to go?
Yes.
Yeah.
All right. I'm so glad my machine is working with some degree of efficiency. It just reduces my stress substantially. Okay, do you remember where we are?
Yeah, the axis defined by the icosahedron's 12 vertices introduce 6 great circles. We already have a pattern with 6 circles, octahedron, vector equilibrium, figure 14.4. However, this is an entirely new set, out of phase, with the earlier group as defined by the jitterbug transformation in 14.7. Outlining 12 pentagons and 20 triangles as opposed to 24 isosceles triangles, these arcs present the most symmetrical arrangement of 6 great circles. When a vector equilibrium contracts into an icosahedron in the jitterbug transformation, the radius edge length equivalence is lost.
Richard, could you pause for a second? What page are you on?
I'm on my 213, but that's not right. I'm on the page that has the diagram 14.7.
Okay, good. Hang on. Okay, there's 14.8, so you're still on 14.7. And what were you just reading?
Just go back.
I'm sorry that I got
right
off.
there.
Okay.
Whoa.
Okay, good. It was kind of screwing everybody up because I got behind you, and I apologize. So go ahead and we'll
It's
catch
okay.
up.
At the top of that page that starts with the earlier group, I just
Good.
finished reading that.
Okay.
And so let me see where I want to start then. Well, I'll start with
maybe you restart at the axis defined by the icosahedrons.
There we go.
Yeah.
Sorry. Go ahead.
We can't see it.
Okay, the axis defined by the icosahedron's 12 vertices introduce 6 great circles. We already have a pattern with 6 circles, octahedron dash vector equilibrium in figure 14.4. However, this is an entirely new set out of phase with the earlier group as defined by the jitterbug transformation in 14.7. Outlining 12 pentagons and 20 triangles as opposed to 24 isosceles triangles, these arcs present the most symmetrical arrangement of 6 great circles. When a vector equilibrium contracts into an icosahedron in the jitterbug transformation, the radius edge length equivalence is lost, but the distances between adjacent vertices on the surface are suddenly all equal. All an icosahedron produces the most symmetrical, no, as an icosahedron produces the most symmetrical distribution of 12 vertices on a closed system, it follows that the same is true for their corresponding 6 great circles. Next, the axes of symmetry connecting the centers of icosahedron faces generate 10 great circles, while the 30 edges spin out 15 more. 6 plus 10 plus 15 equals 31. The total number of great circles in the limit case pattern, figure 14.8. These circles provide the spherical edges of a pentagonal dodecahedron, as well as those of an icosahedron, and, less predictably, also include the octahedron. These relationships will be explored below.
Okay. We have about 25 minutes left. Maybe let me see, let's common denominator. I think it might be good to pause here and just do our takeaways. What do you think?
If we stop here, we have to restart
we could start right here. But it's
least common denominator.
Yeah, we'll start here next week. Unless we want to continue. The trouble is that less common denominator goes on it continues for a couple pages.
No, we can stop here. My suggestion was to restart from page 238.
I see.
I agree. So that this 14.8 can be explained a little more.
Do we want to start here next week?
Yes.
Yeah.
We need to start just under figure 14-7.
14.7.
All right, good. I'll put a marker
just
right
under
here
that.
then.
That's where we need to start.
Good. We'll start here next week.
I would like to suggest that we still have 25 minutes.
We do.
Yes, that will give ourselves 5 minutes of discussion on the last one and on figure 14.8. I have a
Right.
little thing to say about it before
Yeah,
we
that's why I
before
suggested we
before
stop.
yes before we share our takeaways.
Good. So let's begin our takeaways. Manu, which figure do you
So
want to talk about?
what I say is so we allocate 20 minutes to takeaways, and then we spend 5 minutes having a discussing about the last paragraph that
Well,
we read.
let's have our discussion now, and then let's have our takeaways.
Okay.
What figure do you want to discuss?
That 31 grand circle. I want everybody. I have a method of remembering it that I would like to share. I don't know if
You have a what?
a method for knowing what the 31 great circles of the icosahedron are.
Okay, good. Go ahead.
Okay. Do you remember from cosmometry the music stuff? Where do you remember that figure where it has an hexagon and a pentagon in the circle? And where we talk about the phi and the 11 notes? We remember that the angle at the vertices of the hexagon of each vertex of a hexagon is 60 degrees. And we remember that the angle at the vertex of each pentagon of the pentagon was 72 degrees. 360 divided by 5 is 72. Now, consider 12 degrees. Because at the conclusion of that, it says you could subdivide, the minimum subdivision that you could have was in how do you call it? In not arcs, in angles of 12 degrees. What is 12 degrees in relationship to the pentagon and the hexagon? Is the maximum common divider of the two. Or the minimum, something like that, is the common divider. So you can subdivide your space that is represented by that 360 degrees in 12 degrees equal to speak the music of universe. Now, take 360 degrees, divide by 12. What is it? It's 30. 360 divided by 12 is 30. That is, if you take a sphere like this, you could cut it with 30 great circles at 12 degrees to each other. 12 degrees longitude, is that?
Yes.
Yes. 12 degrees longitude. But then you have one magic one. That is the equator of a system.
Of what?
The equator.
The equator.
It's the GMT. It's the GMT.
Yes. The equator is a great circle.
Right.
30 plus 1 is 31 great circle of our icosahedric understanding of what we see of our stable universe. And it allows us to map the Earth the way we know by defining the meridians and by defining the whatever is the Capricorns, the latitudes.
Mhm.
So if you take it this way, the first 360 degrees, you are defining the meridians. If you take it the other way, like this,
Mhm.
you are going to define the latitudes.
Mhm.
And that was the
The
point,
only
you know, like,
the only great circle in the latitude is the equator. Any other circle
Mhm.
of latitude is not
no,
is
I'm just
not.
saying, I'm not talking about great circles there. I'm just talking about orienting like this.
Okay.
You still is a great circle. It's like this. I
Cool.
don't know how to show it. If I took it like this, still going through the center, but I go 12 degrees each.
Mhm.
Yes. I was talking about that in application for our orientation, how we navigate our seas or our line.
Cool. Are you complete?
Yep.
How are you feeling and what are your takeaways today? Thank you for sharing that, by the way.
Okay. I'm feeling quite happy that I've been able to board this train, because when I came in, you guys were already at the cruise speed. I don't know how I survived landing into it, but that's fine. You provided for me a landing space for me there to land. Uh, what I take away is what the discussion that we have in regard to what Lee said. We should always have in mind general principles in building our anti-entropic devices for
Mhm.
whatever purposes that we may entertain in this world. Because if we do it, we stand a better chance of going the way Anne is going with schooling, with education.
Mhm.
Because you cannot entertain general principle without seeing the line of flow that affects as universally as we can imagine the things that are around us. And that's my biggest takeaway. It might not be just like it adds a dollar to my pocket, but it is to me something that is that sets apart those who do great things in this world. Is the ability to see bigger first and align it at that level before they come to the applications. And the applications are going to be more efficient in any way. For example, the electric vehicle. You have to imagine that, well, energy is energy, you generalize energy. So if we're using thermal energy for motor cars, it should be possible to use electrical energy that is cleaner, that is more efficient into the automobiles, considering all of other constraints that we have, pollution and all these things. It is only by thinking that way that we can build a winning world. So that's my takeaway. Otherwise, I'm grateful and I'm privileged to be amongst all of these people. I don't know what the sum total of all the experiences here, not overlapping now, but they are huge. I don't know, Richard's talking about when you retire from faculty, Richard, actively, that is like 20 years ago.
Yes.
and it's been accumulating another thing. Steve is there in China. I don't know what Chinese. I've actually never been to continental China. I've been Taiwan, but in Hong Kong. But we have a feeder there. Joe is there. I met Joe. He's cruising the East Coast there, doing his own things. And Lee is there, coming with a general contractor's experience. It's such a diverse world and such a rich world and such a nourishing world. That's what I take away. Joe, you haven't talked about a lot. How do you feel? What do you take away?
I think it's actually been pretty interesting, and I think what you just said there a moment ago, actually, Manu, was really important. By kind of understanding generalized principle and understanding the macro, allows us to be in a position where we can work on particulars and specifically work on the distribution of of energy and weights. And you think about it in those terms, that's something where you can start to think about how in systems there is a certain degree of well, you're using energy effectively, so you're able to do more with less. And there's also an idea of redundancy that is built in. And that's one of the important things when you're thinking about how, when you're structuring even, organizational structures, and even I would say, local economies, is that this idea of how you're distributing your energy enables a certain degree of robustness, and all of that is coming from your ability to start to apply generalized principles. And that's something that I think is often overlooked. I think we often get focused on parts, on one specific thing, and we kind of get out of balance. And personally, I have that issue. That often happens in different areas. So when I think about these circles that we're the way we're talking about them, and the idea of stability, that I start to I think about it in terms of how it can be applied at the systems level, and there can be a certain amount of resilience built into an organization, or any kind of structure, really. And ultimately, you can see the basis when you look at it from that perspective. Is what you really can see here is Bucky's ephemeralization coming to life. That's the most important thing. When you start to see, when you're starting to allocate energy, efficiently, and you have a certain amount of redundancy built into a system. But it all starts with, Lee's, questions and your points about generalized principles and being able to apply things at the macro level, as opposed to being stuck in our own world doing things individually and not necessarily working harmoniously together. So, Anne, how do you feel? What do you take away from today?
A lot. My goodness. First, I want to say thank you to Steve for sharing this the 3 videos. Yeah, I think the
that
YouTube
too.
videos is amazing.
I should have said thank you for that.
Yeah. And then Richard, I'm gonna go check in on what you mentioned about this quantum city. Yeah, that's happening in Canada. Yes.
Yes, at the University of Calgary. Yes.
University. Okay, I'll go check that out, because it's resonating with me what you're talking about there. And then Manu, how your mind works, and Fred too, both of you. The way your mind works, minds work, both of you. I want to say thank you, because you, and for taking the trouble to really dig so deep into the sciences for us, and the mathematical part of it. And then Joe and Lee, today I got so much out of both of you as well from the things that you've shared. I was kind of quiet for a bit there for about the whole thing, But to end this, I've been I've been asked to speak when the Alibaba people come to our school on February the 4th. Okay, so and it occurred to me that how I'm thinking right now is very precessional. So thank you very much, guys. It's and so when I speak about, because we ask the question, who's the higher authority than the university? That's very precessional, right? If you can figure that out, then you can work backwards. And then with the content I got from comparing world games and WTP, right, the World Teams Parliament, right? What came out is that it's a question that I'm dealing with, because I do get pushback from parents all the time, other schools and all that. They tell us that and then after that, 5-10 years down the road, everybody's like, wow, this is crazy. And then other schools started to use the things that we do, from dodgeball to entrepreneurship to etc. Right. So I just want to share that precessionally, right? We have a way to introduce the children from kindergarten, primary, and secondary, at least the foundation of it, and to build them to become the designers of future systems. Okay, and then to think at planetary level, so that they are regional stewards of civilizational thinking, right? So if we know that together we can create this foundation to build upon, I don't know. I even if parents push back, I cannot go backwards and pretend I don't know this, and that's the kind of community I'm in, culture I'm in, which is Malaysia and Asia, right, where you have a ton load of people who will push back, right? So when we went down the path of doing this with Alibaba, we expected one of the schools to have more of a pushback, but it's the mid-tier ones who are, the pushback was highest there. And so I had to figure out a way to answer them. But I just want to say thank you very much, because moving forward, I think we will have more like organizational level, as in companies and all that, who will come on board with this precessional direction that we're taking. Okay, that's what I'm going to add. Thank you very much, everybody. So next one, Fred, how do you feel and what is your takeaway today?
Who?
Fred.
Fred dropped off the call.
Oh, right. Sorry. Okay, then. Lee, how do you feel and what's your takeaway today?
This has been a joyful time for me. I have learned an awful lot because I could associate what I have learned and didn't understand to now what I have known about, and that is in general construction, from building a school, using circles and triangles and everything that I've learned, and finding out that I've been doing mites. You know how awful mites were to me to start with. I couldn't understand anything about it. That is wonderful. And Anne, you talking about those people that go backwards, it's because they're not understanding going forward, and they need assistance to understand, using what they understand as an example and bringing it into the future. Let's see, who else? Steve, are you the last?
Richard, I think, is next.
Oh, Richard.
Yeah.
Richard, what is your, how do you feel and what is your takeaway?
Well, I'm feeling very interconnected to several things, but part of it started with Manu talking about anti-entropic, and it brought to my mind again this whole question of being holistic and starting with the whole rather than starting with the parts and trying to work to the whole. And so for me, the default position that we've all been sort of taught in some ways is you start with anti-entropic or with entropic, the breakdown. And then anti-entropic is the sort of counter to that. The other way of looking at it for me is that we start with syntropic, which is the integration, and anti-syntropic is the entropic. And it's just, to me, it's the big difference between the mindset that we use, that's our default mindset, that traps us into the old way of thinking. And so I'm reminded of wanting to start with the whole, which means I want to start with the syntropic, and then I can blend in the anti-syntropic that has to do with breakdown and the importance of parts in different ways. So that was a takeaway for me. The other takeaway is Lee talking about her background experience in construction and the importance of triangles and squares and that sort of thing. And I've been associated with a group that started in Australia called Mates in Construction. And it has to do with the way we used the polyhedral tetrahedron to construct a way of building a social construction to help people in the construction industry to minimize their risk for suicide. And so it's an interesting parallel when you think of how buildings are built with triangles and other polyhedra, and how we've taken the same triangle concept, the tetrahedron, and the triangles out of that tetrahedron and turned them into a way in which they become helpful to mates in construction, the people in the construction industry. And it started in Australia out of work we did in Canada, and now it's being field trialed in the United States as a possibility of a Australia program being transplanted into an American program. So it's a full circle. Talk about great circles. Something that started in North America, went over to another continent, and now it's coming back. Now,
just like Jimi Hendrix.
Yeah, just. And the other one is with Anne talking about the pushback and so forth. Just before Christmas, I was connected to a teacher in Vietnam in an international school. Turns out she's a Russian-Ukrainian background and has been in that part of Asia for quite a long time. And she and I are now starting into a dialogue about how Fuller's work might be applied to the educational system. And I did tell her about Anne, and I just got a note from her today, and she's intrigued about what Anne is doing. But she's got another set of eyes, if you want, on the influences of Fuller's kind of thinking and whether or not it can be applied in systems other than what I'm telling her. I've been trying to apply it. And so I really think there's a potential for some really interesting dialogue because she's really concerned too about new ways of thinking in the educational system that get resisted. And she's trying to figure out a way to move beyond that. So that's another takeaway in terms of these interconnections along the line of what Manu was talking about. Oh my gosh, connected to someone in mainland China, to Malaysia, to the US, to South Africa, to Canada. Yeah, what as I've said to a number of people, sort of my kinds of tribe, my soulmates. And in reference to when I retired, which is in 2004, so it's now more than 20 years, I keep saying, where were you guys when I needed you 25, 30 years ago? And and I think I might have mentioned it, but in the year 2026 is the year that we wrote a futurist paper in 1988 to say what my profession would look like if we had adopted Fuller's ways of thinking by the end of the last century. Well, we didn't really adopt his thinking, but the paper is now ready to be read in the year that it was written for. So that's going to be kind of fun for me to relate to different people about what we thought the future would be like 38 years ago. So, Steve, back to you, and what are your thinking and your takeaway?
Wow. I'm sad that Fred is not here because I'd love to hear his takeaway, and I'm certainly grateful for Fred kind of tracking through on the meeting, putting important comments in line and his contribution. So I'm going to miss him right now because he's included in my major sentiment. I can't believe this group of people that I'm involved with in this call. God, I'm so blown away by each of your contributions to the universe in your own regional stewardships, to quote Anne. It boggles my mind, actually, and I'm honored to call you my best friends, and so I'm excited. So my takeaways are, I just have been reminding myself about the significance of topology, and as I went through that, I showed you the video about the electrons and the Pauli exclusion principle. And oh shoot, now I got sidetracked by it. But these electrons of the topology, shoot, I just blew it because I tried to go back and do it. So maybe I'll come back to it. But I'm really excited about, in the electrons, one of the four elements that created the topology of the electron was angular momentum. Anyway, so I'm finding that all of these things kind of fold into each other in some major ways. What I realize here tonight is that the isotropic vector matrix is a theoretical model of reality the way it really is. It's theoretical. And at some point, the electrons were a theoretical model, but we've been able to take pictures of them. So suddenly, an electron is not so theoretical anymore. There seems to be something actually called an electron. And it's possible that with this CERN experiment, although I'm sure it's on the edge of some reality, because Stephen Wolfram has also created nodes and edges and interactive things, where Stephen Wolfram actually can show the formation of a black hole with his formulas. And so this idea of a node and connector matrix is coming up now on several modalities. Maybe one day it will not be totally theoretical as it is now. I loved, for me, we got this, electrons would be theoretical, except now we can take pictures of it. And so what we have is electrons are composed of fields that interweave together to create the matter that we experience. And it's just mind-boggling. And of course, it is mind-boggling. The brain can't even comprehend it. One of my big takeaways here is, I'm grateful that Joe's back from Italy. He made it back safe. And he's got this European ambiance, and so I'm grateful for that, Joe, too. The thing that my big takeaway, Anne, was this idea that we are regional stewardships of civilization. Wow. I want to be an individual steward of civilization. That's what I am. And I'm thinking, like, how can I say that? Because while you said that, Manu contributed that his reference to the idea of cosmic integrity. So what I am is I'm a individual and thus regional steward of cosmic integrity. But hell, you say that to somebody and they think you're a weirdo, right? So I've been trying to think of some synonyms, because maybe I'm maybe I'm an individual steward of civilization's good, but how about system integration?
Nice.
I'm a regional steward of system integration. And they say, what the hell are you talking about? Well, we got electric vehicles out here, and this whole concept of that whole concept, we want to integrate that into what we're doing in every aspect of our deal. What is true about electric vehicles and that grid that we can apply in other systems too? And instead of isolating ourselves and saying, well, we know what's cool in our region, we have our own systems in our own region. We want to integrate civilization. We want to integrate systems. We want to be stewards of cosmic integrity. So there ought to be some ways to say that without looking like a total weirdo. And I'm looking for ways to say that without looking like a total weirdo. So anyway, and I'm just thrilled about this call. I wish we could hear from Fred, but we'll hear from him soon. Any other comments or questions before we go? Manu. Oh, hey, Manu, while you're talking, hold up your cube octahedron. Hold up your IVM, please. I'm going to pin you up here and take a graphic of that because I want to make sure that, hold it up a little higher, please, and hold it off to your right. Move it to your right, a little further to your right. Oh, good, because we're getting rid of the file cabs and things behind a little bit more, and I've got it. I've got the isotropic vector matrix made by Manu. Go ahead, Manu. What do you want to say as we close our door here?
Okay. Do we understand all that the Pauli's principle of exclusion is another statement of the general principle of duality, the way we understand it?
Yeah, it is.
It is exactly that. In our duality is not opposite. It is the intention of being hidden to let the other guy shine and do it alternatively. That is exactly the principle of exclusivity of Pauli. In terms of quanta.
Cool.
That's what I wanted to share. It's exactly that.
Cool beans.
And it goes with what Richard is always saying. It is not opposition. It is us to learning the ability to let the other guy speak and to listen and take heed of it and make it constructive and playing that game. The pulsative nature of universe is that one. Making that game. It's an infinite game, basically. Because we play it like that, it becomes a principle.
Mm-hmm.
Yeah.
Very cool. Okay, looking forward to our next meeting. Anne wanted you to send something via WhatsApp if possible.
Yeah, I'll do it that way.
Thank you.
All right, everybody.
All right.
Until next time, thank you for being my friends.
Bye-bye.
Thank you.
Bye-bye.
Take care.
Bye.